The last time we left off, we had derived what is commonly known as the Cahn-Hilliard equation. So you see it, this is the Cahn-Hilliard equation. And what we're going to be doing today is trying to understand what the implications of this equation are, and how to understand what kind of evolution you get from an equation that looks like this Cahn-Hilliard equation. So in general, this gradient energy coefficient here that basically tracks the energy associated with gradients in the system, and the mobility here can be functions of composition. And in fact, if you remember the definition of the mobility, which, so this mobility basically involves all of these terms here, this capital M. And you can see that we're going to take all of this stuff to be a constant, independent of composition. And so that's an approximation right off the bat. But nevertheless, that's what we're going to do. And so we'll start with the Cahn-Hilliard equation. We're going to write it in one dimension again for simplicity. Is going to be equal to the mobility. We'll take it as a constant so we can pull it out. So you have the divergence, which in one dimension is a derivative. So m, you pull the m out, then you have a derivative. d by dx of the in one dimension. So you can pull the derivative through. And then do it again, and you end up with an equivalent form, assuming again k and m are independent of composition. Looks like that. Okay, so the thing that makes this a little interesting is really this term here, because remember the free energy is a function of composition, kind of looks like this, and so it's pretty clear that this term here is a function of composition. This is some function of composition. Okay. Composition, and you see that this function of composition multiplies the derivative of c with respect to x, and so this is a nonlinear term. So this is nonlinear. Whereas this term up here, the gradient term, is just the fourth derivative. K is a constant independent of composition, so this is a linear term. So that's a little bit easier to handle, numerically, analytically. So the question is, how do we solve this? How do you solve that equation? And if you think about all the methods that you were taught when you were an undergrad, involving things like separation of variables, Fourier transforms, Laplace transforms, they don't work on this equation here because of this nonlinearity. Take a Fourier transform of a product of two things, and it does not work all that well, at least in the classic way of doing it. This afternoon, Guru will show you how you might do this numerically using Fourier transforms, but you have to do some tricks in order to get it to work. So what to do? How do we solve this? And so we're going to consider a simple limit. Simple limit, where we have we're going to look at what happens where we start a uniform composition, C0, and look at and consider small fluctuations about C0. So in other words, what we're going to do is we're going to consider the case where you start with an alloy of a certain composition C0 and ask the question, will perturbations grow or shrink? And the idea here is that these are going to be small fluctuations. And so that enables us to linearize this Cahn-Hilliard equation up here. Oops. This Cahn-Hilliard equation up here. Okay, so specifically what we're going to do is we're going to take C as a function of x and t to be equal to C0 plus a small parameter times a perturbation function C of x, C tilde x and t. So epsilon here is a parameter which is much, much less than 1. 10 to the minus 2, 10 to the minus 3. We don't know what it is, but we just know that it's much, much less than 1. And so what we can do now is to plug this equation here into the Cahn-Hilliard equation. And so, for example, dc dt is equal to C0 plus epsilon C tilde x and t. And so the time derivative of the first term, that's a constant, is equal to 0, right? And so you get epsilon with respect to t. Similarly, the other linear term behaves in the same way because it's linear. It's going to be epsilon fourth. The crucial term, the key, is this term here, is that nonlinear term. And what do we do there? Well, we know that this second derivative is a function of composition, and so we have to linearize that too. So you have the partial of f, the second derivative is some function of composition, and you write that as a Taylor series expansion plus the partial with respect to c squared. By definition, the Taylor expansion, it's evaluated at C0 times the C minus C0. And if you use the definition of this perturbation function that I've given on the top here, you plug this into here, the C0s cancel, and you get C tilde is a function of x and t. And so now we can use this in the problem term. That was this had the second derivative, and you just use that Taylor expansion, which I give here, and you put this into there. So you get d by dx of and then you have the derivative, the first derivative, which is just epsilon partial c tilde with respect to x, because the C0 cancels. Okay? And so this becomes C0 epsilon partial c tilde with respect to x plus times this third derivative of f with respect to x times the partial times epsilon squared with respect to x. Right? Look okay? Okay, and here's the key thing. You notice that this term is of order epsilon, and this term up here is of order epsilon squared, right? So let's say epsilon was 10 to the minus 2. So this is 10 to the minus 2. This is 10 to the minus 4. And kind of an assumption we're making here, if you want to be really careful mathematically, is that all these other terms, oh, that should be C, sorry, is that all these other terms here are kind of order 1. They're not 10 to the 4th, right? They're kind of order 1. So this term here is small compared to this term here. And so we can say that we can neglect that term if you choose epsilon sufficiently small. So you just neglect that term. And so then we can plug this, we can put this all together. We can put this all together, and we get epsilon partial c tilde with respect to t is going to be equal to m epsilon c0 right? So it's all those terms, and you kind of know that you did the perturbations right because all the epsilons cancel, and now you have an evolution equation for the perturbation. You have an evolution equation of the perturbation. Okay, so that's the math, that's the algebra and how you do it. But let me just kind of step back here for a second. So let's go back. So in the original Cahn-Hilliard equation, we had something that looked like this. It looked exactly like what I just derived, very similar. The only difference is that here, this term is a function of composition, whereas this term is evaluated at the initial composition. Okay? And so basically, now, rather than having this term be a function of composition, it's a constant. It's actually a constant. And just to make life easy, what I'm going to do is I'm just going to second derivative minus 2k. Looks like that. Okay, so f double prime. All right. So the question here is how do we solve this? So what in the back of our minds, what we're doing here is we're starting with a composition profile that looks like C0, and it can be some sort of composition profile at t is equal to 0. Some sort of fluctuation of the composition profile at t is equal to 0. And we're going to ask the question about how that composition grows in time. How that composition grows in time. We're going to solve this on an infinite domain. Infinite domain. We're going to say that the derivative of c with respect to x goes to 0, and x goes to plus or minus infinity. So everything's kind of well behaved at infinity, and so we're going to use Fourier transforms. If you were doing this, for example, solving this in a finite domain, you'd use separation of variables and not Fourier transforms. You get sums of sines and cosines rather than integrals. So to kind of refresh your memory about how Fourier transforms work, so you have c as a function of x and t. Minus infinity. The Fourier transform I'll call capital phi. Okay, or the Fourier transform of the composition field in the definition that I'll be using has, you put the 1 over 2 pi here in the front. Dx. Okay, and so to take the Fourier transform of, we start by taking the Fourier transform of the linearized Cahn-Hilliard equation. The linearized Cahn-Hilliard equation. And you take by taking the Fourier transform of this. So you do that by multiplying by e to the ikx, dividing by 1 over 2 pi and integrating. And so you, for example, if you look at the time derivative term, you will have a 1 over 2 pi times the integral from minus infinity to infinity, the partial c tilde dx. And so you can pull that out, the derivative out. Dx. And so that's equal to 1 over 2 pi dt. Okay? So you basically, the partial derivative of t just kind of pulls out. 1 over 2 pi. You have this other term that looks like this of partial 4c e to the I kx dx. Let's do the first one here. Let's do this squared. So the way you do this is that you integrate by parts twice, right? Everyone don't remember that. You integrate by parts twice, and basically the kind of mnemonic way of understanding what the Fourier transforms does, when you integrate by parts, what you do is you just take one of the derivatives and throw it onto this term here. So you integrate by parts, you take a derivative of this, and you get e to the ikx. Ik e to the ikx. You take another derivative, and you get ik squared e to the ikx, so you just get minus k squared. And so this thing becomes minus k squared over 2 pi. And then you basically get back the Fourier transform. Okay, and so the same thing for this term. And you can see that why linearity is important, because that integration by parts trick wouldn't work if things are if you have nonlinear terms sitting there. And here you get k to the fourth. You just basically get the k squared terms squared by k and t. So you can put that all together, and you get. The neat thing about Fourier transforms is what it's done is it's taken a partial differential equation and reduced it to an ordinary differential equation. So you got rid of the spatial derivatives and replaced them with a constants k, basically the wave vectors k. And so you end up with m pi. So this is a simple ordinary differential equation that is easy to solve. So remember, this Fourier transform is a function of k and time, but it's a function of time in particular. That's the important thing I want to emphasize here. And so you need an initial condition. You need to know what the fluctuations look like at t is equal to 0. And I don't know what they are, but I do know that if you give them to me and they're regular, reasonable functions, you can write it like this. You could just take the Fourier transform of it, right? Right? So I give you whatever that initial condition is. So the key thing here is, the 0. This is the initial condition. And so now that you know what the initial condition is, you can solve this differential equation here. It's just an exponential, and you know what it is at time t is equal to 0. The Fourier transform at time t is equal to 0. So you just get ik times time. And now you know with the Fourier transform, you can write the inverse transform and determine exactly how this function, how the fluctuation will evolve in time. Any questions? Comments? Yeah.
So d phi by phi is equal to minus m. That's something you could do.
Yeah. Okay. Let me do this.
So you get logarithm of phi plus some constant. The constant is at time. Right?
It's a separable ODE, right? So you have that, and then you get log phi is equal to the right-hand side times t. Take the exponential, and put you have a constant plus a constant, yeah, that you can put in full in front. Okay, thank you. Okay, so at first glance, this is a problem, right? It says, well, I can tell you how this perturbation will evolve in time. I can tell you how this thing will evolve in time, as long as you give me its Fourier transform. And that's pretty boring, right? I mean, how do you know what that fluctuation looks like? And if it depends on that fluctuation, what good is this really? But if you look at it a little more, what's really important is not this, it's really this. And this is the beauty of Fourier transforms of linear equations. It says that I can give me whatever Fourier transform you want, right? So this I is a function of k as some function. I can tell you whether that wave vector k, or the Fourier transform of that wave vector k, grows or shrinks by just looking at this term here. It's independent of this. And so what you want to think about this is that you take the Fourier transforms, you get sines and cosines, and each of these sines and cosines decay or grow depending on this factor here. And they do it independently of each other. Right? So a sine of k1 and a sine of k2, the k1s and k2s, the different wave vectors, decay independently of one another, strictly dependent upon this exponential term. Okay? And so to a certain extent, this doesn't matter. But if you ever wanted to actually watch how these compositions evolve for a very specific initial condition, you can plug it in here, take the Fourier transform, if you can, analytically. You'll get you'll get this. But since it's linear, the only thing that matters, since linear, each Fourier mode, the way that the technical way of saying is that each mode decays or grows independently from all the others. Which implies the only thing that matters is t. And in fact, it's really basically whether or not it grows or shrinks Depends on the sign. Fourth. Okay, so before I turn the page, I want to also point out something. If you go back and look at this equation here, or this, you'll see that the linear theory says that the growth rate of a fluctuation will go exponentially in time, with an amplification rate given by this term here. But it's exponential. It's not a power law. It's exponential in time. And that's one of the predictions of the linear theory of spinodal decomposition, that you have this exponential growth in the fluctuation amplitude. And so the whole discussion can be basically boiled down to this term here. It's already, I'm just repeating the equation that I had before, so there's no need for you to rewrite this in your notes. It's basically that, which is called the amplification factor, for example. And you can write this as the diffusion coefficient, remember, is m times this second derivative. So you can write this as the diffusion coefficient times k squared. Fourth. Okay. So the amplification rate is a function of k. Okay, so if you remember the little sketch of a derivation I did when we were talking about the diffusion equation, I had basically these first two terms here, the diffusion coefficient and the wave vector squared. So if you consider the case where d is where f double prime is greater than 0, the diffusion coefficient is greater than 0, so this term is positive, this is positive, of course the wave vectors are positive, and so that means that q is always negative, and you get something that looks like this. That's the classical diffusion. And this is why your numerical code that you wrote yesterday worked quite well for positive diffusion coefficients. If you're within the spinodal and f double prime is less than 0, if f double prime is less than 0, this becomes positive, negative. So this whole term here is positive. That's positive. So for small k, this term's going to dominate, and it's going to look like a parabola, and it's going to be pointed up like this. And that was the bad thing that was happening to your diffusion code when d was negative. But you see what happens up here. F double prime is negative now, and so this term is negative. This is again positive. So at sufficiently high wave vectors, this thing turns around and it does this. And there's actually a critical wave vector here where it crosses 0. Okay? And so if instead of using the classical diffusion equation, you had used this Cahn-Hilliard equation, what you would find is that your code would not blow up. Because you can see now that as k goes to infinity, q is negative, so all the fluctuations will decay for sufficiently large amplitude. Okay? So why is that? So why does this gradient energy coefficient affect these high wave number fluctuations? And the way to see that is to look at what a composition profile. So that's the composition profile of a certain amplitude, certain k. And let's say you increased the wave vector, which decreases the wavelength, but it has the same amplitude, right? So you look like this. So you can see it has the same amplitude, But now look at what's happening here. The gradient is higher than it is here. And so what happens when the gradient goes higher? Remember, we put in this gradient energy effect that said the higher the gradients, the more it increases the energy. The gradient energy coefficient is positive. So what happens is the energy goes up, and eventually the system says, I don't want these high wave number fluctuations or small wavelength fluctuations. So the system decays at large k. So it's due to this gradient energy effect. So basically the gradient energy effect, the way you can save you, and what you'll see in the mathematics literature is that the gradient energy coefficient regularizes. Basically, it makes it now a well-posed evolution equation rather than this thing that blows up at sufficiently small wavelengths. Okay? So there's some important things that you have to, the other important things here. So if you look at this, there's a wave number with the maximum growth rate. So we can define Kc is where Q at Kc equals 0. Km is defined as where the derivative of Q with respect to K equals 0. This is the wave number with the maximum growth rate. And why is the wave number with the maximum growth rate important? Because if you look back here at this equation, it's growing exponentially, right? And so there's a certain wave vector Km that gives you the maximum growth rate, and it's growing exponentially. And so you would expect to see in the system fluctuations that grow, and eventually what you would see is these fluctuations be of the wavelength or wave number Km, because they're growing exponentially, and the Km is the thing that maximizes this growth rate Q. So if you wanted to get an estimate, an order of magnitude estimate for what the length scale is, it'd probably be something around Km or Kc, but certainly something around Km is what you'd expect to see. So Km, wave number, maximum growth rate. And if you have k greater than k sub c, the critical wave number, Q is negative, and all fluctuations shrink. And if k is less than k sub c, Q is greater than 0, and all fluctuations grow. All fluctuations grow. So Kc is given by, as I said, you can determine Kc because Q of Kc equals 0. And so that implies that F double prime equals 0. Equals 0. And so there's two solutions at k sub c equals 0, which is basically this case down here, which we're not interested in. And we're interested in the one at non-zero k sub c, which would be this one. So you get k sub c is going to be equal to minus the 1/2. So the other interesting thing that, of course, this equation implies is that in order to have, oh geez, the minus sign should be on the inside. Sorry. In order to have a well-posed square root, F double prime has to be less than 0, right? So basically you have to be within a spinodal. F double prime is less than 0. dq, decay, km, you set that equal to 0, and you get 2km F double prime plus 8k q equals 0. So that's km F double prime plus 4k 0. And that again gives you for the non-zero km is the interesting one. or 4k, which is equal to k sub c over the square root of 2. Okay, so what does this mean? And I'm going to draw some pictures here. So if you solve the Cahn-Hilliard equation in one dimension. Oh yeah, there's an interesting story about this, interesting anecdote. So when John Hilliard joined Northwestern in the 60s, his first graduate student at Northwestern was a now distinguished, very distinguished scientist by the name of Didier Desfontaines. And his PhD, his entire PhD thesis was solving the Cahn-Hilliard equation in one dimension. That's all he did. And that was enough for a PhD back then. You folks will be doing the Cahn-Hilliard equation in 2 dimensions this afternoon. Okay? It's pretty amazing. So say we take we have a phase diagram that looks like that with the miscibility gap. We cool down through the critical point, let's say, and we have a certain alloy composition C0, and you have composition C beta E, C alpha E. As a function of position, like this. And we start with a small fluctuation, and we know that this fluctuation is going to start at some small amplitude, let's say, and it's going to grow exponentially, and it's going to have the wavelength of the fluctuation with the maximum growth rate. That's what we just kind of. And then what happens is that as the amplitude begins to get bigger, the assumption that we made when we derived the linearized version, that epsilon is much, much less than 1, that this fluctuation is small, breaks down. The equation becomes nonlinear, and so you begin to get shifts in the wavelength as the amplitude gets bigger, and as time goes on, eventually you end up with compositions that approach the equilibrium composition C beta E and C alpha E. Okay? So that's a sketch. I'll show you some pictures of how this evolves in a second here. And in fact, you'll be able to produce much more realistic ones this afternoon. Questions? Everyone see that? And so the reason why this composition profile here, that one, goes to the equilibrium values, has to do with the fact that this partial squared f with respect to c varies with composition. If you didn't have that, these compositions would diverge to infinity and you wouldn't have, right? Okay. I want to emphasize one other thing, and this is kind of a fun illustration, a hand-wavy illustration of the importance of these things. They're sometimes called dispersion curves. You'll notice that for wave numbers greater than k sub c, q is less than 0. Q is less than 0 in that region. Okay? So imagine you're doing spinodal decomposition in a small particle, let's say, and this small particle has a radius r, where r is much, much less than lambda c divided by 2 pi. Okay? So in other words, the radius of your particle sits out here someplace if you put it on in a wave number space. So what would happen to that particle? Would you see spinodal decomposition? Probably not, right? And so this wave number here kind of gives you an order of magnitude length scale. If the domain is too small, then you might not see spinodal decomposition. That's a very hand-wavy kind of way of using these dispersion curves. You can ask more careful questions about, well, do you have absorption at the surface and other complicated things that might come into play. But it kind of gives you some idea of the importance of these length scales. And you can see that you have an amplification rate that really is very long wave. 0 wavelength is 0k is infinite wavelength, right? So it's basically the size scale of the system. But it has a very low amplification rate, so you don't see them. So let me show you some pictures of spinodally decomposed structures. Okay, so This is the initial state of the system. And so what we're doing there is that we're already in the very late stages of the phase separation process, where the compositions of the two phases are nearly at their equilibrium values. So it very quickly evolves from this initial state to one that's given by the equilibrium compositions. And you can see you have a highly complicated structure. One of the things I want to point out here is you can see that you have lots of particles and separated domains. That turns out to be an artifact of 2 dimensions. If you do the calculations in 3 dimensions, and you just write an equation, you write a visualization code that only visualizes the value of the order parameter or the value of the composition in the interface right between the 2 phases, okay? So you have this space that has a composition that goes from C beta to C alpha E. You say, show me all compositions that have the value that's halfway in between, and draw that. That's the picture that you see here. And so in 3 dimensions, you get structures that look like this. So it's highly interconnected. It's called bicontinuous. You can move from one end of the structure to another and never leave one phase. And it's very, very topologically complicated. People have thought about these for models of phase separation in the early universe to nanoporous gold structures when you have corrosion of a certain alloys. So what about the linear theory of spinodal decomposition? The best illustration of this that I know of goes back to some really interesting work done in the 80s, mid-80s, by Hashimoto. And this was spinodal decomposition of these 2 random copolymers. And what he did is he measured the scattering intensity. And the nice thing about X-ray scattering is that it measures the amplitude of a composition fluctuation of a given wave number k. So he's using q here as wave number. This is not the amplification rate q that I just mentioned. And so this is wave number, amplitude. You want to measure is amplitude. And so at early times, you start off with some nearly uniform composition profile. And as time goes on, you can see that the wave numbers of a certain value increase in time. And so this is the wave number with the maximum growth rate. This is exactly what spinodal decomposition, the linear theory, would tell you. Then at later times, that the fluctuation with the maximum amplitude begins to shift to lower values of k. And this is this nonlinear regime that I'm talking about. That once the amplitude becomes too bigger, you get nonlinear effects that move this. And so to emphasize that, in fact, linear spinodal theory of spinodal decomposition works, this is the log of the amplitude as a function of time. You should remember these are growing exponentially, so you should get straight lines. And in fact, you get straight lines for different values of the wave numbers, basically. And so it's completely consistent with the linear theory of spinodal decomposition. To the best of my knowledge, no one has been able to do this with metals. And remember I said at the beginning this linear theory of the theory of spinodal decomposition depends upon the interaction range between atoms. And so one of the claims is that this interaction range between atoms is too small for this continuum equation to work at these early times. Because what people see when you do it in metals is you always see this. You always see the amplitude kind of moving in time rather than being independent of time at a given wave vector. But that's if anyone would like to do ultra rapid quenches in a synchrotron, maybe we can revisit that problem. But right now, that's kind of the status of the field. So I want to return now to what these composition profiles look like. And you notice I kind of sketched this one here, but I want to kind of blow it up a little bit. So you start with these small fluctuations. The small fluctuations grow, and in one dimension, what you'll eventually end up is composition profiles that kind of look like this, where you have far away from the interface, you'll have the equilibrium compositions of the phases. This is one dimension. You'll have and then in between you'll have a transition zone. And now you can see why we're talking about this. You probably lost track after 4 hours. Is that this is like a phase field method, right? So you have a diffuse interface between the two phases, and it's of great interest to understand what sets that distance delta. Because what we have in the I should have emphasized this in the pictures I showed you, is that remember in the 2D pictures you had particles growing and shrinking. You're actually solving this free boundary problem where you would have to mesh up the interface and apply boundary conditions that depend upon the curvatures and all sorts of complicated things like this by just solving this one Cahn-Hilliard equation that's valid in all space. Okay, that's the advantage of the Cahn-Hilliard equation and the advantage of a phase field model itself, is that it captures the limit where these are the equilibrium compositions, and you have an interface in between. And so these interfaces can move, they can join together. That's not a problem. You probably saw that in the 2D calculus. Let me just. So let's look at this one again. Okay. So now it's kind of phase separated. You have particles with composition nearly equal to the equilibrium composition of beta, equilibrium composition of alpha. And if you wanted to solve this using a sharp interface model, like I sketched at the beginning, you'd solve a diffusion equation in here, a diffusion equation in here. You'd mesh up this boundary. You'd put mesh points on the boundary. You'd measure the curvature of the boundary, and that would set the Gibbs-Thompson equation, or chemical potential at the boundary. And you'd have to do this in all the boundaries. And then you'd have to march it in time. And that's why the sharp interface model basically died. People don't use it. The other thing I want you to notice is that you can have merging. Did you see it? Do you see it right there? So there are examples of merging maybe in this region. I don't know, we'll see. No. They're coarsening away. Sometimes they merge, sometimes they coarsen. You see it? Yep. And so the other thing yeah, there it is. You see it up there? That was an example. So the other thing that the phase field method does, and the technical word of this is topology transitions. So it allows for merging. It allows for particles to disappear. You know, if you did this with a mesh on the surface, what you'd have to do is you'd have the mesh, and then eventually you'd have to get rid of mesh points, and get rid of mesh points, get rid of mesh points until it finally disappears. Then you have to basically excise the mesh out of it. It's just a nightmare of programming. And furthermore, if you have two interfaces that collide, you have to allow the two meshes, you have to merge the meshes together. It's really a hard problem. Here, we just say, I have one uniform grid. I solve the Cahn-Hilliard equation. It gives you all of that for free. All of that for free. So that's one of the real strengths of the phase field model. And it's all, the reason why that works has to all associated with the fact that you have an interface that's diffuse. And this diffuseness is kind of the key idea when you're doing a phase field model, is that you have this interface diffuseness. That's the big advantage of the phase field model, because you solve one partial differential equation that's valid every place. It allows things to merge. It allows things to disappear. It's also the disadvantage of a phase field model, in that you have to resolve that interface. And you have to resolve, and so you have to understand what sets that interface, what sets that interface width, and what sets the profile through the interface. And so what I want to discuss, probably for the last half hour or so of the class, or maybe we'll see how far we get, is how to compute the computing. Okay, planar interface. So again, we're back to one dimension. In general, so just to make life easy, you have the molar free energy as a functional composition. or that you could also view this as the Gibbs free energy as a function of composition. Both get used in the community. And so you have a free energy curve that looks like this. You have a common tangent construction that gives you the compositions. Okay? We're going to make some simplifications just to save algebra and kind of focus on the fundamental physics, really, and not some of this more subtleties that really don't change things. We're going to take that free energy function and we're going to make it look like this. And we're going to choose the reference energies, the standard state free energies, such that that's 0. And basically, if you use this representation over here, a lot of the constants in the equations that will be deriving disappear. If you want to look at the more general case for here, this case here, it's in the original Kahn-Hilliard papers, and so nothing that I'm doing will be changing any of those results. It just makes life easy and it keeps us focused on what's really going on. So we know that in this particular system, the total free energy, Ft or Gm, is given by the area times F is a function of C plus K dx. Okay. So in the system with the interface, you have all of this. You have all of this, and the free energy of the interface is the excess energy associated with the interface. And so we have to subtract from Ft the energy associated with uniform composition. Interface. Okay, so in other words, what I'm saying is that if you had these phases and they were uniform right up to the interface here. Okay, so in this case, if you look at this case here, right, so the compositions are uniform, you have no gradients, right? And what is the energy associated with the alpha phase of composition C alpha E? 0, right? Same thing with beta E, and that's basically why I chose that free energy function, just to make life easy. And so that means that so sigma, which is equal to the free energy of the non-uniform system per unit area, minus the free energy of the uniform, or the energy without the interface, no interface. That's 0, and so this is equal to 0. It's equal to 0, and so sigma then is just equal to the minus integral from minus infinity to infinity. Ff is a function of C, so the area moves to the other side. Oh wait, okay, sorry. So you may be wondering why I put the area here. Okay, so this is a free energy. This is a free energy. That's a free energy density times a distance, which is a free energy per unit area, times an area gives you a free energy, okay? Because we're considering a 1D profile here, okay? So the A is the area of the interface, sorry. Basically the cross-sectional area of the interface. Okay, so let's stop and think about what this means. Let's stop and think about what this means. So, okay, so we have our free energy function. So the free energy density is a function of position. And then we have our free energy, our composition profile that we think probably that looks something like this. Okay, so if you've never looked at these before, they're somewhat confusing. Okay, so what does this mean? So think about what's going on. So you start, let's say, out here, start all the way out here. The free energy, you're sitting down here. The free energy is 0. And as you begin to move along here, the bulk free energy of a bit of material of this composition, so there's a composition, you go over and you pick up the free energy. And as you go through here, now you're in the middle, you're up here, then you go over to here, you come back down the other side, and eventually you end up over here. So as you go from one phase to another, you traverse, you go from here up and over the hill and back down. Okay? So the free energy of the interfacial energy has to be related to the free energy function in this region here. Okay? So that's the first thing. The other thing that's kind of interesting that you can think about is if you look at this composition here, you go over to here, you go up, you're within the spinodal. So is that composition stable or unstable? Is this thing stable or unstable? And the answer is it's stable because you have this gradient energy coefficient, and we'll show that in a second. So the gradient energy coefficient allows these compositions in here to access the spinodal, which is where they're unstable. So the interfacial energy, sigma, is going to be given by a minimum in this integral from minus infinity to infinity. It's the lowest energy for a composition profile. Okay, and so it's also very helpful to understand what's really going on here. And I'm going to contrast that to what each of these terms mean in this integral. So so let's say you had this case here. Okay. So if I asked you the question, how to minimize this integral, you say, okay, well, let's minimize this term first. Okay? If you want to minimize this term first, you would like all the phases to be in this phase, all the compositions to be in right here or right here, right? So it would look like this. But then if you look at this term here, what's the derivative of this step function? It's infinity, right? So you get an infinite contribution here. And so the system says, no, I don't want that. If you just look at the gradient term, if you were just a gradient person, you'd want the whole thing to look like that, right? No gradient. But the problem there is that you really want to capture these equilibrium profiles on the other side. The equilibrium compositions on the other side. And so you have a trade-off here between this, which likes things to sit down here, it doesn't really like this part of the free energy curve, and this, which likes everything to be uniform, which means it doesn't want to sit in these two both well simultaneously. Okay? And so what you get is a trade-off somehow between this. And this trade-off is the composition profile that you actually see in the system. That's a trade-off between the uniform and the step function. Okay? And how do you determine that? Well, again, you do that using the Euler-Lagrange equations. You basically look for the composition that minimizes the energy of the system. And so we need the composition profile. That minimizes the interfacial energy, and that's given by equals 0. And we already have that before. We did that once already. It's the partial of f with respect to c minus zero. One thing I note here, I don't have lambda, I have 0, because what we're interested in here is we're going to enforce conservation of mass by saying that the composition phase compositions. There we go. At plus or minus infinity. Basically, what I'm saying is that we're going to enforce the fact that far from the interface you're in the bulk phases, and that basically enforces mass conservation for you enough. So this is the Euler-Lagrange equation. For the equilibrium. C is a function of x. And then you take that C as a function of x and you plug it into the expression from sigma, and you get sigma. Okay? So that's the approach. So this gives you the equilibrium composition profile. I'll go back to this in a second. So you solve the Euler-Lagrange equation. It gives you this composition profile. You take that composition profile and you put it back into this equation here. It involves f to c in that derivative. You do the integration and you get the interfacial energy. Okay, so that's the prescription here. To do that, I'll show you there are a couple of tricks along the way that make life easy. So let's integrate the Euler-Lagrange equation. Integrate the Euler-Lagrange equation. So you take dc equal to some constant. So the first one is just f as a function of c. The second one here you can rewrite. Do a change of variables in the integration. Equals a. And then what you realize is that d by dx of is equal to that, which is exactly what we have here. And so you can replace that term with 1/2 of that. Equals a. And so again, that's just, you can do that integral now when you write it like this. Equals a. And then we're going to say that as x goes to plus or minus infinity, dc dx goes to 0. You're in the bulk phases. 0. And f of c goes to 0 because you're in the bulk phases. And that implies that A is equal to 0. And the Euler-Lagrange equation has this equivalent form then. It looks like this. Equals 0. Or f of c squared. And then you can put that back into the expression for sigma. And you get the expression for sigma as 2k dx. And so this equation here turns out to be quite useful in a phase field model, because basically it says that if I have I don't need the free energy function in order to get the interfacial energy, right? It's independent of the free energy function, which is kind of cool, and it only depends upon the derivative. And so that's very helpful when you derive your phase field models and you want to compute the interfacial energies. The other thing that's important, of course, you can see is k here. So if you don't have a gradient energy coefficient, you have no interfacial energy. It's kind of a key thing. So sigma is proportional to k, and there's no f as a function of c. So you don't need the bulk free energy function anymore. You just need the actual composition profile, and that kind of makes things easier to do when you're doing things numerically and you have a complicated phase field model. This is directly extendable to multi-component systems, for example. It's actually in the original Kahn-Hilliard paper. Okay, any other questions? Yeah.
Will this work for other free energy functions?
Other what?
Other free energy functions. Ginsburg window.
Oh yeah. This is generic. That's right. Yeah. Oh, okay. What? So it will work on any free energy you need. Okay. Okay. Speaking a little quickly. These are good questions. I want to make sure everyone understands. It works for any free energy function that's continuous from one phase to another. Right? It has to look like this. So it can be a Ginsburg-Landau. It can be regular solution. It will work. The problem becomes, and we were talking a little bit about this yesterday with some of you, is that if you look at a Calfat free energy function, they typically, or more general free energy functions. Remember, the assumption of the phase diagram is that they had the same structure, and that's a pretty limited set of phase diagrams, really, and they mostly look like this, where you have FCC, BCC, or solid liquid, or something like this, where you have two phases, alpha and beta now with different crystal structures. And this free energy function here, you can see already what the answer is going to be. It's strongly dependent upon this thing, right? If you didn't have that, you wouldn't have an interfacial energy. So the question is, what do you do with that? And so what people do typically, so you put another order parameter here, and you can extend this into 3 dimensions and make it continuous. So in 3 dimensions, this is a 3-dimensional. You extend it in an order parameter, and this order parameter is 0 and 1. And when it's 0, you sit down here. And when it's 1, you sit up here. And those minima sit in this 3-dimensional space. So you have one minimum that sits out here, and you have the other minimum that sits out here. And when you project it into that 2-dimensional space, it looks exactly like this. And since it's now continuous by this way that you've put these two things together, these two free energies, you can take all the derivatives, and everything else works. But what you're doing is you're adding this artificial parameter. You know, everything that we've done has been very careful about talking about the physics and all this kind of stuff. Here you're just adding a parameter, an indicator function that takes you from one phase to another arbitrarily. And you could worry about what that does to your physics, but nevertheless, that's what you do. So that's a that's a very good question, because that's a problem clearly if you don't do something about it. And the first paper that did this, you'll see it in the kind of the alloy theory community, with some work by Kachaturian, for example, many years ago. In the solidification community, people didn't try to derive these from first principles. They just put together an indicator function, and some nice work by Wheeler, Bettinger, and McFadden in the solidification community use this idea. So but it's basically the same idea. Okay, and there's lots of care in choosing that interpolation function in phi that you have to do in order to get the right answer. So you just can't kind of pluck it out of the air. Okay, great. So we'll see. That was a very good, very helpful question. So please, see you in about a half an hour now. Okay.